in case of the PocketQube class student satellite development in Hungary. And I would like to talk about our developments, not only the 5 by 5 by 5 centimeters PocketQube, but the 5 by 5 by 10 centimeters 2 PQ size ATL1 and the further SMOG-1 satellites. So after the development of the first Hungarian satellite, like Mossad-1, which was 10 by 10 by 10 centimeters 1 unit CubeSat, when we are operating this first Hungarian satellite, we decided to continue the satellite development in Hungary, integrated in the education system at the Budapest University of Technology. And a new group of students decided to form a new satellite development group and make the potentially the second and the third Hungarian satellite, which are PocketQube class satellites, like 5 centimeters cube and ATL1 5 by 5 by 10 centimeters. So the main aim of the SMOG project is to monitor the DVBT spectrum. So there are a lot of DVBT transmitters all around the world, and we want to measure the radiated radio frequency signal during the orbit, during the pass over the Earth, and we want to record its signal level from the 460 megahertz to 860 megahertz frequency band, where a lot of DVB-T transmitters are working because of the high resolution DVB-T signals, like terrestrial broadcasting system in case of the TV. And we developed a special spectrum analyzer on board the SMOG type satellite, and the first aim is this electromagnetic pollution monitor system, and we want to create an electromagnetic pollution map from the Earth. The secondary payload of the SMOG satellite is a total ionizing dose measurement system, and after the break, Gabor will talk about this total ionizing dose measurement system to be able to monitor the health of the satellite because of the ionizing dose radiation caused by the sun. The onboard electronics suffering from this dose radiation, and we want to monitor the life of the onboard electronics. And third payload, in case of SMOG-1, because of SMOG-1 will on about 650 kilometers above the ground next year with Soyuz-2 rocket, and between the solar cells and the side panels, we mount a special hysteresis material to decrease the orbit lifetime, because this orbit has at least 18 years in space, and we want to decrease the time of space debris, because after the right operation of the satellite, for example 1 or 2 years after the onboard electronics lifetime, the satellite is a space debris, and we want to decrease this time. And after, for example, 4 and 5 years, we want to decay to the atmosphere. So this spectrum monitoring satellite has a single point of failure tolerant system, and it contains cold redundant onboard subsystems inside the cube. So this is the block diagram of the satellite. the beginning of the energy bus is the primary electrical power system with 6-time redundancy because of the side panels and the solar cells covering the cube. And these primary EPS forms and supply the unregulated energy bus. And the blue boxes, like the central electrical power system, contains the hardware elements which are responsible for the power control unit to be able to form regulated energy bus, like 3.3 volts with enough current limit to be able to supply onboard computers, the real-time clock and calendar, the totalizing those measurement system, the motion sensor system on board, the onboard computer PCB, and of course the communication subsystem and the spectrum analyzer system. And this cold redundant system is necessary for the health of the satellite, because during the operation there are a lot of reboot and switch over to another redundant pair in case of power control unit, in case of onboard computer and communication system, because of the radiation caused by the sun. And during this type of orbit, we are suffering from this radiation effect. And if there are any particles on the semiconductors, we can make it can make short circuit in case of the power control unit. We are able to detect this effect and switch off the, for example, OBC1 and switch over to another redundant pair and continue the work on the orbit. So during the SMOG development, another way of satellite development in Hungary is started. So this is the ATL1, like 2 PocketQube class type satellite with 336 gram mass. And this satellite is, the main aim of this satellite is to test special thermal finial layer insulation materials covering the onboard batteries. So in case of ATL1, there are 4 onboard batteries on board the satellite, and these type of lithium-ion batteries covered by these 300 micrometers thick special thermal insulation, thin layer insulation materials to be able to regulate the temperature of the onboard batteries. And during the qualification process, we tested all of these type of PocketQubes in a cooperation with BHE Corporation. And after the shaking test, we put these satellites to a thermal vacuum chamber, and we have done the baking test because of the requirements. And last year in September, these SMOG-P satellite and ATL1 satellite are integrated in the ALBA pod in a cooperation with ALBA Orbital. And after the 6th of December, after the launch from Mahia Island, from New Zealand, with Rocket Lab rocket, we are working, and we started to work during the orbit. And Now we are operating this type of satellites from the primary ground station at E building of BME with the suitable antenna rotator both in azimuth and elevation angle, because of the low Earth orbit requires this type of antenna rotation to be able to help the satellite in the main lobe of this type of parabolic dish antenna with this 4.5 meters diameter and the 8 degrees main lobe width, and with this backfire type circular primary radiator. It is important because during the past the satellites SMOG-P and ATL1 rotating, and the polarization axis is changing. So it radiates single linear polarized electromagnetic waves, and we can receive with this circular polarized receiver antenna system, and without fading effect of the signal because of or caused by the polarization of the radiated signal. So we are able to track the satellites and control the satellites with more than 600 watts radio frequency transmit power on the 70 centimeters radiometer band. So the satellites are working on the 437 megahertz radiometer band according to the radiometer frequency regulations. So the bandwidth limit in case of the downlink is up to 60 now 20 kilohertz, and the control bandwidth is up to 12 kilohertz, and we are using GMSK modulation, Gaussian minimal shift keying modulation with the communication subsystem and the ground station, and we are able to communicate, not only receive but control the satellite during the lifetime of SMOG-P, and in the morning ATL1 is visible. So I can show our web-based software-defined radio signals when SMOG-P is over Budapest. We can record a lot of data with 1 kilobit per second, 2.5 kilobit per second, and 5 kilobits up to 12 kilobit per second data rate, uncoded data rate, and you can see the satellite control signal in the screen. And if we are controlling ATL1, you can see also the received data packets, the received signal from the satellite, and you can see the normal telemetry signal here, and of course the satellite control signal radiated from the building E. And the fourth payload of the satellite, we are using a special repeat accumulate forward error correction encoder with its iterative decoder system, thanks to Hungarian guys, Hungarian mathematicians like Miklós Maroti, and these bit error rate curves shows the capability of this forward error correction. So if we are using this type of error correction system, we are able to track the satellite with its minimal configuration of the satellite reception, like a single ground station with manual and handheld 6-element single Yagi antennas made by the space qualified measuring tape and measuring rod. And if we are working and running on a single laptop, on a single PC, like the SMOG client version 2 program, we are able to receive SMOG-P and ATL1, and in the next year the SMOG-1 signal from the space radiated from the satellite. And I can show you some telemetry data during the lifetime of SMOG-P. This is the battery voltage of the satellite. The first half of the lifetime, you can see some different energy mode with different consumption on board the satellite. And after the degradation of the onboard solar cells, we so the second part of the lifetime is in a special energy mode to be able to collect enough energy from the solar cells, store in the onboard battery, and with lower duty cycle of the transmit, we are able to operate. And I can show you the temperature of the onboard battery in case of SMOG-P during the lifetime. So the average temperature is about 13 centigrade degrees, due to the health of the battery on board. And we measured the DVBT spectrum with the onboard spectrum analyzer of the SMOG-P type satellite. So the main payload was the DVBT spectrum analyzer, and we made the global electromagnetic pollution map from the Earth on the DVBT band. So if the satellite is over Arctic, there is no signal. So we are able to test the noise level of the measurement system. And for example, if the satellite is over Europe or over Asia or America, we can receive not only DVB-T signals from the radiated 8 MHz bandwidth digital video broadcasting terrestrial TV signals, but the mobile communication system signals over or more than 300 megahertz frequency band. And if we are collecting this type of spectrum measurements data, we had formed the electromagnetic pollution map of the Earth. So it is published about 3 months ago, and SMOG-P had been decayed in the end of September this year, and ATL1 is still working, but maybe there are no further orbit. So ATL1 this day or in Saturday will be decayed, so it will burn in the atmosphere. SMOG-1 satellite, which is in Rome in a group of Unisat 7 team, in an Italian satellite development team. These guys are making 32 kilograms bigger satellite containing at least 8 PocketQubes on board the satellite. And with the Soyuz 2 rocket from Russia, this launch will be in March next year. So it is under integration. And thank you for your attention, because the time is